Now let's talk a little bit more about where this magnetization is sort of coming from. Well, it comes basically from atoms and nuclei. So magnetic properties of material depend on magnetic dipole moments of individual atoms. We consider magnetic materials to be composed of a collection of atomic dipoles which may align with the field or against a field. Unlike electrical dipoles, however, we cannot break the north and south poles, so no monopoles will exist. So we consider magnetic moments to be tiny current loops, right, inside the material itself, right, that is caused by the circulations of atoms while they orbit the nuclei. So for example, if this is a big material, you can divide each of them into like tiny bar magnets having a north and a south pole. Whereas this is just basically giving you, each of them can be considered as tiny loops that are causing these magnetic moments. So first of all, let's start with a very simple model of an atom and see if we can come up with magnetic dipole moments for it. So if we were to consider a very simple atom, you would consider a nucleus in the center and an electron going around the nucleus, right? That electron going around the nucleus is the one that's going to be the moving charge for our case, right? So let's see if we can come up with that orbital dipole moment. So in this very simple model, we will have a nucleus in the center. We will have an electron that's going around the nucleus, right? So the mass of the electron, if I call it ME, and the radius that it goes as is, I'm going to call this R, and the speed that this electron is going at, I'm just going to call it V. You could also call it VE, doesn't matter, right? So this electron, while it's orbiting around the nucleus, I'm going to be considering that as a current loop. So I can call it a current loop, right? So I know that the current that this electron will cause is going to be given by, in general, dq over dt. But in this case, if I only consider one time that this electron goes around, it'll have a charge E and a period t. I also know that the distance that it will travel through is going to be 2 pi r, right? And the speed that it's going to go through is going to be 2 pi r divided by t, where t is the period. So in fact, I could replace this t over here to give me EV over 2 pi r. Then I know that the magnetic dipole moment is given by IA. So this means I can plug the value of E in here, EV over 2 pi r, and area of this loop will be pi r squared. So I can solve it and simplify it to give me ERV over 2, right? Pi goes away, R goes away, and I'm left with the magnetic dipole moment of ER speed divided by 2. This is now called the orbital magnetic dipole moment. And why is it called the orbital magnetic dipole moment? The reason is because it is due to the orbital motion of electron. It is due to the orbital motion of this electron around the nucleus, right? Okay. I also know if I wanted to replace it to look like that equation over there, I can rewrite this orbital magnetic moment as ERV over 2, multiply and divide both sides with m. What do I get? E over 2m mvr. And what is this mvr? It's nothing other than angular momentum. So this equation can also be reduced down to this is angular momentum. And this is the angular momentum of the electron moving in a circular orbit about the nucleus. Now, instead of calling this mu e, I can sometimes they also call it mu L. And the reason is that this orbital magnetic dipole moment is in terms of the angular momentum of the electron as it rotates around in a circle. Another important thing that might not be very necessary, but it's a good idea to know. So angular momentum in quantum mechanics is measured in terms of h over 2 pi, where h is the Planck's constant. So when you are talking about quantum mechanics, the same expression above will now become equals to E over 2m h over 2 pi. Okay? So that's also another interesting fact, that actually the angular momentum, the magnetic dipole moment in quantum mechanics comes from this particularly simple expression. So we've not done anything majorly new here, but it just kind of follows through. And if you were to plug in the values for all of these, like actually the charge of an electron, h, the Planck's constant, whose value is 6.63 times 10 to the minus 34 joule seconds, and the mass of the electrons, you will find that this comes out to be 9.27 times 10 to the minus 24 joules per Tesla. And that is what I pretty much said in the last video, that that's what it's going to be. Another thing that's very, very interesting is, how do you measure magnetic dipole moments? Well, the way you measure magnetic dipole moments is by passing a beam of atoms through a region in which there is a uniform B field. So we know that a net force will exist if we place a magnetic dipole in a non-uniform magnetic field. So the atoms will be deflected from their original paths when they pass through this region. So in the 1920s, experiments showed that atoms with orbital momentum dipole moments of equals to 0 were still deflected by magnetic fields. And people couldn't understand that. Why would that happen? This suggested that there must be another thing contributing to the magnetic dipole moments of atoms that caused this deflection. So in this case, they figured out that this was coming from magnetic dipole moments of the electrons themselves. And those were called intrinsic or spin magnetic moments. So electrons in different states of motions have different orbital magnetic dipole moments, but all electrons have exactly the same intrinsic magnetic dipole moment. Now that we've talked about atomic magnetism, now let's talk about what happens inside the nucleus. Well, the nucleus is made out of protons and neutrons. Protons and neutrons are in an orbital motion themselves under the influence of their mutual forces. They're not literally just stuck there, but they're actually moving in there as well. So in this case, we discovered that this system has two magnetic moments, and the magnetic moments is actually a combination of two things. One, it is the orbital, just like that of an electron going along the nucleus. It is due to the motion of the protons. And number two, again, it is intrinsic. And this intrinsic magnetic moment is due to the magnetic moment of the protons and the neutrons themselves, basically due to the quarks that they are made out of. For example, proton is made out of the UUD quark, and the neutrons are made out of a UDD quark. Those themselves are moving around in there, and they have magnetic moments inside them. However, typical nuclear magnetic dipole is very, very small as compared to when we are talking about atomic dipoles, and so we almost consider them to be negligible as we talk about magnetization of an atom. So one place where nuclear magnetic resonance, or NMR, is used is called the MRI machine, or magnetic resonance imaging machine. What happens in this case is when nucleus is subjected to an electromagnetic radiation of a very precise frequency, it causes the magnetic moment of the nuclei to change. So what we can do is we can align this nuclear magnetic moment in a sample of material by static magnetic fields. So dipoles reverse direction upon absorbing these electromagnetic radiation, and those absorptions can easily be detected by putting them through a machine like this, or called the NMR machine. And this is the basis for nuclear magnetic resonance, or MRI machines, right? They are much safer than taking pictures with X-rays, because all you're doing is you're aligning those nucleuses inside, taking a picture, and then when you let go of it, they will go back to their ground state.